All right, I guess we'll go ahead and get started. It's about noon time. We're moving on from chapter 7 and 8 today, though I want to share just a couple examples of Sn2 and Sn1 reactions in biology. We're going to begin with chapter 9 today, and we'll probably finish that on Wednesday. So what I've drawn for you here at the top, and don't worry about copying these down. Some of these structures are in your text. They'll be in the notes in any case. On the left, you have noradrenaline or norepinephrine, which is a biological precursor to adrenaline or epinephrine. And your body synthesizes this. And the last step is attachment of a methyl group to this nitrogen. Now, if you look at what's happened, we've just made a bond between what used to be a nucleophile and some carbon, and so you might imagine that a great way to do this reaction would be to have some kind of methyl group attached to a leaving group, and to do this via an Sn2 reaction. However, the typical leaving groups that we might think of based in chapters 7 and 8 aren't necessarily useful, or at least desirable for this process. For example, if you decided that you wanted to use methyl iodide, that would work, but it might also modify the oxygen, and it would certainly modify your DNA, leading to all kinds of undesired outcomes, including and up to, but not limited to, death, right? So nature doesn't use methyl iodide for this purpose. I'm getting distracted. I'm almost going to draw the Jolly Roger, so we're going to move on from there. Instead, nature's methyl iodide, one of them, there are actually multiple ways that nature uses to install methyl groups. But nature's methyl iodide is this thing called S-adenosyl methionine, or SAM. You're going to find in biochemistry and in cell biology that there are things, biomolecules with names that if we named all of the bonds in them would be way too complicated. So we give them shortened systematic names, but then those are too complicated, so we give them short names just like people, SAM. And you have to get used to living in a world of acronyms when you're in biochemistry. That's why we're teaching you what the bonds are now, so that you can more easily function in that world. So this is an abbreviation for the structure I'm drawing. I wasn't quite through with the adenosyl portion. If this looks suspiciously like something in DNA or ATP, that's because it is. This is the adenine base that's present in your DNA and your RNA, and that's present in ATP, and I think I've drawn that correctly. So the adenosyl portion I'm going to highlight here. That's adenosyl. And the S comes from the fact that the adenosyl group is attached to the sulfur. Oops, I guess I didn't want that adenosyl there. Now we're moving stuff all over the place. Come on, there we go. So this is the adenosyl group. That's a combination of the base adenine and the sugar ribose. That's where the os in adenosyl comes from. The S comes from the fact that the adenosyl group is attached to the sulfur, and then this lovely portion of the molecule, which I guess I'll highlight in green, is called methionine. I didn't like how I highlighted it, so I'm going to try again. So this is the methionine portion. Methionine is one of the 20 amino acids, happens to be the amino acid that starts, that the start codon codes for. And it, in this case, combined with the adenosyl group, makes a really large leaving group that takes the place of iodide. So, like I said, you're going to love this. Everything I'm circling which we're now going to highlight, I suppose, in fun orange. All of this stuff, except for the methyl group, is a good leaving group. How could you tell it's a good leaving group? Well, it's the conjugate base of a decently strong acid, but what happens in nature is that the nucleophile, as in the case above, would be the amino group from noradrenaline, will attack the methyl group, backside attack. Sorry, I need a red arrow. Backside attack on the methyl group. We break the bond between methyl group and sulfur. The electrons go back onto sulfur, which gets to now be bonded to only two things with two lone pairs and gets to have zero formal charge. So I'll draw for you the, we'll erase a bunch of stuff here. This is the leaving group. Oh, I didn't mean to erase all of the adenine ring. Oh well. And there's the electrons that used to be in the bond between sulfur and the methyl group. This happens to be called S-adenosyl homocysteine, which is not one of the 20 standard amino acids, and this has to be recycled and reconverted into SAM before it can be used again. But the basic mechanism here when that molecule is used is a simple Sn2 reaction. Nature goes out of its way to have good leaving groups that can't do other undesired things. All right. Why are we talking about this? Just because it's a biological example of Sn2. Dr. Price, do I need to memorize or be able to draw from memory that structure? No. Is it going to be on the test? Why would I tell you that? Is it really important? Everything I say is important. Any other questions? You good? All right. So it does the question is this substitution, but it doesn't substitute? Yeah, the thing that gets substituted off is this great big leaving group, and the product of the reaction gives you a new bond between nitrogen and the methyl group. The astute observers among you are going to notice that the nitrogen started with 2 protons. And so at some point there was probably an intermediate that looked like this, where the nitrogen had a positive formal charge and it got deprotonated by some base along the way, but I figured why worry about that at this point. Okay, so that's one example of substitution chemistry in biology. There are a lot of other examples of Sn1 reactions involving carbocations in biology. I told you that in the lab we don't tend to use Sn1 reactions very much, but biology uses them a lot to make carbon-carbon bonds. So here is an example of a starting material for an Sn1 reaction in biology. It's called dimethyl allyl pyrophosphate. The pyrophosphate is this portion of the molecule. And as before, this is our good leaving group. It's a good leaving group because it's the conjugate base of a strong acid. The other reason it's a good leaving group is it's almost always chelated by magnesium 2+, which sort of neutralizes the negative charge. The reason this is called dimethyl allyl pyrophosphate, do you need to know that name? No, of course not, because this is the allyl carbon. And when the alpha carbon, the one that has the leaving group, is also an allyl carbon, then that's a clue that Sn1 can occur, because if the leaving group up and leaves, guess what you've got? a resonance stabilized carbocation. Now, some of you have seen similar problems like this, I think, on the study guide or practice exam, where this whole good leaving group was maybe chloro or bromo, and you maybe said, why can this mechanism go through Sn1? And the answer is because the carbocation that's left behind is not a true localized primary carbocation. Instead, it is resonance stabilized, and therefore is an interesting and legitimate Sn1 intermediate. And you can draw a resonance structure where the positive charge is in between, is on the carbon by the methyl groups, or as an alternative. Okay, so this can be an electrophile in a lot of different Sn1 type reactions. One of the most common is for this pyrophosphate group once it has left. And there are a lot of different ways to abbreviate it, but I guess I'm not taking advantage. Here's the pyrophosphate group, probably chelated again to magnesium. It's easy for the leaving group to hop off and then hop right. That looks like a lone triad. That was gross. Lone pair is 2, right? It's easy for this to hop back on at the other carbon to make a different isomer, in which the pyrophosphate group, which I'm going to abbreviate with as shown there. And that's a different isomer, and it's useful for different things. Now, that's kind of a boring version of Sn1. Yay, the leaving group hopped off and then went back on. But we can actually use this intermediate to make carbon-carbon bonds. So hang in there, because what I'm about to show you now will probably not make a huge amount of sense until chapter 10. But there are a lot of interesting nucleophiles in biology that are decent at reacting with this carbocation. The abbreviation here again is for the full pyrophosphate group. I'm just saving us all some writing. It turns out that we can use the pi bond of this other molecule as a nucleophile. So there's the pi bonding orbital. And we can have that pi bonding orbital attack the empty orbital in the carbocation. I could draw that empty orbital if you wanted. It would look like the pi 2 of the allyl carbocation system. And that's going to form a new carbon-carbon bond between, and now we've got some interesting choices to make, right? And I'm going to see how you can do at predicting what happens here, even though we're in unfamiliar territory. So I'm going to number the atoms over here in purple, 1, 2, 3, 4, and then I suppose we'll do the same over here, maybe in orange, 1, 2, 3, 4. We're making a new bond because the pi bond is attacking carbon 4. Which of the two available options, 1 or 2, which do you think gets the new bond? One's going to get a new bond, the other's going to get a positive charge, because this reaction involves taking the electrons in the pi bond and bringing them over to be a localized sigma bond. So if you had to choose, which one do you think gets the new bond? You think 1, okay, that's right. You had a 50-50 shot, so were you lucky, or do you have a reason why? 1, 2, 3, 4, and I'll put that positive charge on carbon 2. Okay, any reason why that bond might form between purple 1 and orange 4? Sterics is a possibility. Go ahead. Yeah, more stable. So sterics is a possibility. And then also you get as a product the more stable tertiary carbocation. So the bond goes on less substituted carbon. Think of the alternative, which we won't draw, if in fact we had made the bond with carbon 2, carbon 1 would be a primary carbocation. That's just not a good option. Okay? And then, actually, now here's a biological example of an elimination reaction. Of the many beta protons that are available, most often enzyme will remove this proton in an E1 style elimination. And the product is something that now has sort of the same pattern as one of the starting materials did. That is, we have the good leaving group here at an allyl carbon. And so if nature wants to, it can do the whole set of reactions again to bring in another subunit. As it is, this molecule is called Geranil Pyrophosphate. Do we need to memorize that? No, don't bother. But it is a modified form of a molecule you may have heard of, especially if you're interested in essential oils. This is called geraniol, which is rose oil. Okay? I have some opinions about essential oils that I'm keeping to myself right now, but all I have to say is that I'm not keeping it to myself anymore. All I have to say is that the placebo effect is real, so go ahead and take advantage of it. Just don't pay a lot of money for it, okay? A spoonful of sugar makes the medicine go down. Maybe you can benefit from the placebo effect of a spoonful of sugar. Okay, and tirade. So, a couple of different biological reactions that involve substitution, elimination, carbocations. A lot of this is going on all the time, and later on I may show you how a precursor like Geranil Pyrophosphate can be elaborated to form the exquisite multiple fused ring structures of cholesterol. But before we get there, we got to get through chapter 10 and learn some other crazy stuff. So, chapter 9 is about substitution and elimination reactions, but it answers this question: what if your starting material doesn't have a good leaving group? Can you still do substitution or elimination chemistry? And the answer is no, unless you first turn the cruddy leaving group into a better leaving group. So chapter 9 is about alcohols, and generally you're not going to see in OChem any good reactions where some nucleophile comes along and does Sn2 chemistry with OH leaving. Okay, now that may look reasonable to you. It's just like the alkyl halide chemistry, and we have OH minus as a leaving group, but OH minus is a terrible, horrible, no good, very bad leaving group. And if you don't know the illusion there, you need to go back to your childhood and read a book about a poor kid named Alexander. A lot of his life, though, is not going to make any sense to you because the book was written in the early 80s. So you may see a telephone in there and wonder what the heck that thing is. Circular dial and everything. All right, terrible, horrible, no good, very bad leaving group. Why is it a terrible, horrible, no good, very bad leaving group? Well, first, it is the conjugate base of a weak acid. Water is its conjugate acid, and water's pKa is 16. In contrast, good leaving groups have the characteristic that they are conjugate bases of strong acids. That's generally whose pKa's are less than 0. Okay? So that's the primary reason why we're not going to use OH minus as a leaving group. The second reason is that the bond between the alpha carbon and the oxygen is pretty strong. So it would be difficult to make the reaction thermodynamically favorable. Another example of a reaction that generally doesn't work the way you might think is if you have this ether where the leaving group is not OH minus, but some other negatively charged oxygen. We generally don't do this reaction either. It just doesn't work. Because again, OH minus and OR minus are both terrible, horrible, no good, very bad leaving groups. Same deal, right? See the conjugate acid of RO minus is an alcohol whose pKa is also around 16. So substitution, and we could say the same thing about elimination chemistry, doesn't work that well for alcohols or ethers. So we need a workaround. And there are a number of them, and some are better than others. One of the simplest works around Books of Mormon, life's hacked. Anyway, one of the simplest works around is to use an acid, like maybe HCl, to turn the OH group into a good leaving group. How does this work? Well, acid-base chemistry, which you know from chapter 2, will protonate the oxygen to create this oxonium ion. The reason we know this can work is because the pKa of HCl is like -7 or more, or lower, whereas the pKa of the oxonium ion is -2. So this is totally thermodynamically favorable. And now you've satisfied the criteria for a good leaving group. It is the so you have to pay attention to what it would be if it left, right? It would be H2O is a good leaving group because it is the conjugate base of H3O plus, which has a pKa of -2, meaning it's fine with the electrons it takes with it when it leaves. All right, so now that that's in play, we can proceed to use a nucleophile. In this case, it's probably the conjugate base of our acid, and we can do an Sn2 reaction with this primary primary alkyl oxonium ion, I'm not sure what you would call it, to generate water and the alkyl halide. Now, why in the heck would you want to do that? Last chapter we were using alkyl halides, and one of the things we could make from them was alcohol, so this seems rather a step back. But it's to illustrate the idea that if you turn the OH into a good leaving group, you can do Sn2 type chemistry with it. But there's a complication. And we start to see this complication when you start to move to secondary and tertiary alcohols. And that is, you can try the approach of protonating the OH and turning it into a good leaving group, but you get both stereoisomers. So what do you think that means for the mechanism? It's not Sn2, or at least it's not completely Sn2, because otherwise we should have seen only the inverted product, right? Presumably the first step is that lone pair electrons attack the proton from HBr to generate this oxonium ion where we've got the good leaving group. Of course, if it were Sn2 from that intermediate, we would see inversion of stereochemistry, but because we see both, what that means is likely the OH group leaves to give us a carbocation, and then the nucleophile bromine can come in from above or below. If you think those two arrows don't really look like above or below, you just have to imagine them. I'm just indicating that you're coming from above the page or below the page. So we get both of those products, which is unfortunate because, as I told you, stereocenters are expensive, especially when they're pure. And so we just wasted this lovely R2-butanol and turned it into something that is no longer enantiomerically pure. So sad for us. So there are some other works around that do not result in SN1. When you use strong acids on alcohols, you often get undesired SN1 chemistry. Now, you're right to ask me at this stage, what about the elimination product? Nobody did yet, but some of you were thinking it. In fact, I predict someone is right at this point typing into the chat, what about the elimination product? Shall we see? We're waiting, come on. Well, no takers. It's not funny if I have to tell you. Okay, there it is, Jake Hadfield from the chat. Thank you. It turns out you'd be right to expect the elimination product, and I don't know why they don't show it to you here. There are going to be a lot of nuances in this chapter and in future chapters where things that you might anticipate would be a problem somehow aren't. That's because a lot of these reactions are empirical. The way organic chemists discover reactions is they try a bunch of things and they see what works, and then try to explain after the fact why it works. And sometimes it's hypothesis driven, sometimes they have an idea of what will make the reaction better, but other times it works, and sometimes the mechanism still isn't known yet. So I told you that SN1 and E1 always compete. I don't know why we're not showing you elimination products there. You would be right to expect them. And that's why I generally am not going to give you questions on an exam where you use acid and alcohols to generate products. Go ahead.
So why wouldn't we just imagine that it's an SN1? That it's always going to be SN1 as long as there's what's called an acid or a base?
Could you always assume that it's going to be SN1 as long as there's an acid or a base? I'm sorry, is that the...
Because everyone said like an SN2 product, right? That's what you'd expect in the reaction.
Right. You know, I mean, experimentally, you know it was an SN1 product. What I'm asking is if you knew it was going to go through a carbocationic intermediate, why aren't we seeing our friends, the elimination products? Because I said SN1 and E1 always compete. And the answer is, I don't know. Perhaps they are observed sometimes, but your text chose not to put them here. I certainly wouldn't count it wrong if you showed them as options. I don't need you to memorize the fact that, okay, for alcohols with acids like HBr and HCl, you don't have to worry about the elimination product if it's going to be SN1, except for all the other times when you do. That's not a very good thing to sing to yourself at night, and we prefer nice mantras instead of confusing ones. So we'll accept the fact that the reaction isn't useful because it does go through a carbocationic intermediate, and we'll put on the shelf why we don't see these. Someday, if you're in a lab and you decide to try this reaction against your better judgment, because I told you it was a bad reaction, and if you see elimination products, you won't be surprised. You'll say, oh, those are alternatives from the carbocationic intermediate. Okay. Computer's still alive and it is charging. Okay, I'm at 32% somehow. I'm wondering if all is lost. No, all is not lost. So here are our no SN1 alternatives. That is, these reactions go through SN2. I'm realizing that the way I wrote that was confusing. There are no SN1 alternatives. Over the weekend, we went up to American Fork and our kids younger kids played with my sister's kids out in a park, and as we were driving past on State Street past Mod Pizza, there was a sign up that said, I think they meant to say we're hiring, but they didn't have an apostrophe, so now it just says we're hiring, which is sort of depressing. We were hiring, but now we're not. So it sucks to be you guys. Yes, so these are the so-called no SN1, no carbocation alternatives. They don't go through an SN1 mechanism. So we're going to introduce a new reagent. That reagent is phosphorus tribromide, or PBr3. And it may not be obvious to you why this reagent works the way it does. You can think of this as a phosphorus surrounded by good leaving groups. And so it's not outside the realm of possibility to think that an alcohol could attack the phosphorus. The one thing you might need to understand why this happens is to note that oxygen phosphorus sigma bonds are pretty strong. So are oxygen phosphorus pi bonds. And so it's actually quite thermodynamically favorable to replace a phosphorus bromide sigma bond with a new phosphorus oxygen sigma bond. Doing so converts the OH group into some weird, unusual structure that you might not quite know how to think of. And I wouldn't expect you to say, hey, this is a decent leaving group. But it doesn't look that different from the oxonium ion, where the thing here is a proton, only the thing here is the phosphorus. So empirically, people observed that if you did this reaction, you would get, as a product, the pure stereoisomer here with no loss of stereochemistry, meaning that you observe complete inversion from the chiral starting material into the chiral product. So what does that tell you about the mechanism? Had to have been SN2. Otherwise, you should have seen a loss of configuration. So SN2 with backside attack and inversion of configuration gives us the product. Now, I don't know whether you from first principles could have looked at that leaving group and said, hey, this is a good leaving group, but not good enough for SN1, not good enough to leave on its own, but is okay for SN2. But after the fact, having seen the result, we can rationalize that that must be what happened. And remember, as we think about competition between SN1 and SN2, remember our energy diagram where the leaving group could leave to give a carbocationic intermediate, and then the substitution reaction could happen. Or we could go through the SN2 transition state where the nucleophile comes in as the leaving group leaves. Presumably there's a sweet spot that you can hit where the leaving group isn't good enough to leave on its own, but can start to leave when the nucleophile comes in, at least better than OH minus could have left. And so presumably we're in this area where the SN1 pathway is too high in energy, but the SN2 pathway is okay. All right, questions about that? So that's something you're going to need to know, is that you can use PBr3 to convert an alcohol into an alkyl bromide via an SN2 reaction. Let's see. I'm looking at a question from the chat, trying to make sure I understand it. What I'm talking about is if this were SN1, we could modify the OH to turn it into a good leaving group, and then the leaving group would have left first, and then we would have had a carbocation like we talked about up here. So instead of that, you can modify OH to turn it into a good leaving group, but then the nucleophile comes in and attacks, and the leaving group leaves, all in the same concerted step. Okay. So that's one example of a reaction you're going to need to know. And there are lots of ways to test this type of reaction, test your knowledge in this type of reaction. Let's suppose we have this alcohol, and suppose I ask you to provide the reagents to convert that alcohol into this azide. And suppose I tell you you may need more than one step. So how do you plan this synthesis? Well, you can think, I'm going to do, it looks like I'm going to do a substitution reaction because I'm replacing the OH with something else. Then look at the stereochemistry. The stereochemistry used to be up here, but it's still up over here. So could I do that through a direct Sn2 reaction? No, because Sn2 involves inversion. So that gives me a clue that I'm going to have to need sort of two steps. The other thing that tells me I'm going to need two steps is the fact that OH minus is a cruddy leaving group. So the idea here is, in my second step, I want to use the azide as a nucleophile in an Sn2 reaction, and that means the precursor is going to need to have been something like this, so that azide can come in and attack from the backside and generate our product. But the question now is, what is our first step? Should it be HBr? No, silly rabbit. You guys don't even know. Cereal commercials aren't what they used to be either. There used to be a rabbit that would try to sell tricks, which are actually not that good, but the rabbit was obsessed with them and he never got them, and it's kind of a sad story. No, because we go through a carbocationic intermediate and lose stereochemistry. So if we use PBr3, we can convert the OH into a good leaving group. PBr3 does that. It replaces the OH with the bromide via an Sn2 reaction with inversion. And then we go through a second Sn2 reaction with inversion, and that gives us the final desired product. Okay, see what we did there? Now, the pathway we just did is we proposed a synthesis. It was a simple two-step synthesis, but we had to think about which bonds we were going to make, and we had to think about stereochemistry and how to get the desired stereochemistry. All right, other questions? Yeah?
Why couldn't it be HBr?
It couldn't be HBr because if you use the strong acid, the resulting oxonium ion is prone to having water leave as a leaving group. And that would give you a carbocation intermediate. And at that stage, you just lost your stereo center. Ty, are you raising your hand? No? Okay, sorry. Just yawning. It's hard to tell. I have no context. I can't see mouths. So, all right, other questions? Could you use an Sn1 reaction that gives you both forward and backside attack? Well, that is what would happen from the Sn1 reaction. And so if you tried to use HBr here, then you would end up getting both the desired and the undesired diastereomers, and you would then get a mixture of products in the next step. Okay, so that's one way. Now, in chemistry, we like to have multiple ways of doing things in order to get us out of unanticipated chemistry jams. There's some reactions that don't go well for no particular reason, and so we like to have lots of options. So, introducing reagent number 2 that does Sn2 with inversion. This reagent is called Thionyl Chloride, SOCl2. That may be a reagent you need to memorize. It's going to, like PBr3, turn the OH into a good leaving group. You may not know from first principles how this reagent works. That's fine. The electronegative chlorines make the sulfur electron poor. That makes it easy for the lone pairs on the oxygen to attack the sulfur, probably in the sulfur chloride sigma star, and the leaving group leaves. And that then generates the following intermediate. Now, it turns out that in order to do this chemistry, typically you need to use a base. Why do you not need to use a base with PBr3? I don't know. Empirically, they found it wasn't necessary, but it did make the yield of the thionyl chloride reaction better. Nevertheless, what happens in the reaction is just that Cl-, which left from the sulfur, comes in Sn2 style with backside attack and inversion of configuration to give us the alkyl chloride. Now, I can show you, this is what I want you to know for the mechanism. FYI, I can show you what the base is good for. Probably after that leaving group leaves, you've got something that looks like it has a proton that ought to be pretty acidic. And actually that base, pyridine, can remove the proton. These electrons can kick down to form a new oxygen-sulfur pi bond, and the chlorine can leave. This is kind of an elimination style reaction, if you want to think about it that way. Again, you don't have to worry about this. I'm just showing it for the curious among you. And this maybe provides the thermodynamic sink for the reaction because you just made SO2, which is a gas and can bubble off, and the reaction is now irreversible. So, you know, you may need to memorize that we use SOCl2 with pyridine, although on an exam, I don't anticipate putting as option A SOCl2 and as option B SOCl2 with pyridine. Even if I did, you could figure it out, but I'm not going to do that. And you don't need to know what I've shown you in this FYI box. But you do need to know the idea that thionyl chloride converts the alcohol into the chloride with inversion of configuration. Now, because these reactions all proceed via Sn2, they are useful for primary and secondary alcohols, but certainly not tertiary alcohols, because you can't do Sn2 with tertiary alcohols. And since the whole point of using this reagent is to keep using these expensive reagents is to keep stereochemistry, if for some strange reason you wanted to take tert-butanol and go to the tert-butyl chloride, you could simply use HCl. You're going through a tertiary carbocation as an intermediate, and then chlorine would attack. And there's no stereochemistry to worry about. So if you wanted to do that, you could. But you're not going to use PBr3 or SOCl2 and pyridine on tertiary alcohols, just because it would be a pointless waste of time. Okay. Questions so far? Yeah.
Why does using pyridine and pyrene or whatever not go into the stereo?
Why does pyridine not come in and attack here? So yeah, the question is, how is pyridine able to remove the proton without also being a threat at the alpha carbon? And the answer is, you just need to look at the conjugate base of pyridine, or imagine what it would look like if it attacked the carbon. It would be permanently positively charged. And so pyridine is an example of a base that is not a good nucleophile. We didn't talk about it in chapter 7 and 8, but it is on the list of things you can use as a base that's not a good nucleophile, so you don't have to worry about substitution chemistry. Others? Side of the hand? Yeah.
Can you go to the tertiary alcohol?
Yeah. You can't do SN1 at tertiary carbons. I'm sorry, let me back up and strike that from the record, please. And then say you can't do Sn2 at tertiary carbons. So using SOCl2 and pyridine or PBr3 would be pointless. The whole purpose of using those was to avoid a carbocationic intermediate. But if you want to do substitution reactions with tertiary alcohols, the carbocation is just inevitable. So you would just go ahead and use the approach that we talked about at the beginning that we wanted to avoid, which is to first protonate the alcohol to get the oxonium ion. Then you would wait till the leaving group leaves to give you the carbocation. Then the chloro conjugate base from HCl could attack the carbocation to give you the acid chloride. All right. Others? So I guess in the last couple of minutes, I'm going to introduce method 3 of doing substitution reactions. And this is kind of a fun one because it involves turning OH into a good leaving group without proceeding to do SN2. Notice that our approach previously turned OH into a good leaving group, but then something else came in from behind and did a substitution reaction. So now we've got the chloride, which is a good leaving group too. But what if we wanted to stop here, right? What if I wanted a way to do what if I wanted a way to do the reaction I was showing above, but in a few fewer steps? That was stupid. I'm sorry. I don't know what I'm saying. A fewer number of steps, but that's redundant. What if I wanted to replace the OH group with the azide with inversion of configuration? Our approach earlier wouldn't work, right? Turning OH into the bromide with PBr3 and then using azide would give you the opposite stereochemistry, and you can't use azide directly because OH minus is a cruddy leaving group. So the question is, do we have something that could conceivably turn OH into a good leaving group without immediately going through SN2, generating a stable compound that we could then take on to the next step using azide? And the answer is yes, and it involves a new reagent that we're going to learn about. It is, there's a lot of new reagents that you're learning, and it will be difficult to keep them straight. You'll need to come up with whatever works for you to remember things. This is called Paratoluene sulfonyl chloride, which of course we've now have an abbreviation for, TSCl. And this will work like thionyl chloride, only unlike thionyl chloride, the intermediate we get is stable basically indefinitely. So we're basically out of time, so we'll have to pause there and fill in the details next time. So until then, have a good afternoon, and I will see you on Wednesday.